today we want to talk about sets, symbols, and terminology. There are 3 ways to designate a set. One is using a word description. For example, the set of even counting numbers less than 20. That is a way to describe a particular set. Another way to describe this same set would be using a listing method. Using a listing method, you want to use set notation, which is these curly braces, and just list the values in the set, if that's at all possible. So if we're talking about the set of even counting numbers, you know what counting numbers are. 1, 2, 3, 4, 5 numbers you count with. And you also know what even numbers are. So we're talking 2, 4, 6, 8, 10, 12, 14, 16, 18. Now we include the 20? No, because it says the set of even counting numbers less than 20, not less than or equal to 20. So that is a listing method. And then the third way we can describe a set is with set builder notation. Now the first 2 probably made really good sense to you. Set builder notation is a little bit different. You also use the curly braces, and then you select a variable. We usually use the letter X to represent a variable, but select a variable. I'm going to call it X. And then you have this vertical bar. Now that vertical bar, you can read that as such that. And you would say all the X's such that X is an even counting number. I'm not finished though. Less than 20. So when you use set builder notation, it's really kind of using words and the listing method. So you use the set braces on each side. You stay your variable, and it'll be for every X such that, and then you use that same variable again, and then describe your set as you would a word description. So here's a general way to use set builder notation. So notice the curly brackets, and then I have for all X such that X meets some particular criteria. So this first guy, you could say for all, whatever the variable is. If it was a B, you would say B. For all X, such that, so remember the vertical bars are such that, and then X meets some particular criteria. So let's try another homework problem, or another example. Now, let me point this out too. Most sets are named with capital letters. So notice I named this set capital A. And that's pretty typical to use capital letters to denote a set. So this is called A is all the odd counting numbers between 2 and 20. Now that's a written way of saying it, okay? Now let's write it as a list of elements. So you always use your curly brackets for a set. Now if we're going to use all the odd counting numbers between 2 and 20, the first odd counting number between 2 and 20, we're not going to use 1 because it's not between 2 and 20. So let's start with 3, and then we have 5, 7, 9, 11, 13, 15, 17, 19. Do we go on to 21? Well, no, because it said between 2 and 20. So that's listing the elements. And then if I use set builder notation, you have to use those same curly brackets. Use whatever variable you want. I tend to stick with X. So for all X, such that X is an odd counting number between 2 and 20. And there's set builder notation. So for example, B, we're going to do something very similar. So this time I called the set B also. Notice again it's a capital letter. And in written form, the set of even counting numbers between 24 and 26. So we're supposed to write B as a list of elements. Okay, so that's when we need our curly braces, and we're just going to list every even counting number between 24 and 26. Now let's think about the numbers, the counting numbers between 24 and 26, and I believe there's only 25 between 24 and 26, right? Just the number 25. Problem is, it's not an even number. So if we just list the elements, look, we got nothing in there. And so if you see that, that's another way of saying the empty set. Other notation for the empty set is a circle with a line through it. They mean exactly the same thing. What you don't want to do is this, okay? That is not the empty set. That's the set with the empty set in it. So this is not the same thing. So you either use curly brackets with nothing in between, or you use the empty set notation. You don't combine both of those together. And then finally, write B in set builder notation. So again, set builder notation means we need the curly brackets. You need a variable such that, and then you just list in words what your criteria is. And that's, again, X is an even number, counting number, I should have said an even counting number, between 24 and 26, or you could, again, just say, hey, that's the empty set. Something pretty important about sets is a set needs to be well-defined. What do I mean by well-defined? Well, take a look at this example. Let's list all of the great actors. So I want to know what the set of great actors is. So you start writing your list of great actors. I'm sure you can think of some. But then I might pick an actor that I think is great that you don't think is great, or vice versa. So this is what I would call not a well-defined set. If you are not sure if an element is in the set or not, just because you've got some kind of vague statement here and you can't decide, then that is not well-defined. Okay? But check out this next set. If we talk about set E is the set of all Academy Award-winning actors, you would be able to easily look up to see if an actor fits that criteria or not. So great actors, not well defined. It's hard to say if an actor is great or not, but an Academy Award winner, well, you can tell if an actor fits in the Academy Award winner set or not. So if I extend that a little bit, is Denzel Washington, notice this new notation here, is Denzel Washington an element of D? In other words, is he included in the set D? And again, I might say he is, you might say he isn't, so we can't say. So again, the set D is not well defined. We don't really know if he's in the set or not. It just depends on who's asking, right? On the other hand, is Denzel Washington an element of the set E? Now, if you look that up, or you may already know, it turns out, yes, he is an element of the set E because he has won an Academy Award. So your set needs to be well defined to actually have a clear set. Next, I want to give you some information about sets of numbers. And so we have lots of different types of numbers. We have natural numbers. Notice what's important about natural numbers. It's the numbers you count with. It doesn't include negative numbers. It doesn't include zero, no fractions, no decimals. We're just talking about the regular old guys you count with. 1, 2, 3, 4, 5, and that goes on forever. Those are also called counting numbers. Notice these are identical sets. It's the same exact set. You might hear them called natural numbers. You might hear them called counting numbers. They are the same. Next, we have whole numbers. Whole numbers include 0, so they are identical to the natural and counting numbers with the addition of 0 thrown in. Notice all three of these are what we call infinite sets because they go on forever in the positive direction. Next, we have integers. Now, integers are the whole numbers plus the negative natural numbers. Okay, so natural numbers, you can put a negative in front of all of them. It makes it negative, and that gives you the set of integers. So in, I forgot my ... Those are called ellipses, but I should have had a ... right here. It goes on forever in the negative direction and then goes forever in the positive direction. So after the integers, we have rational numbers. Now, rational numbers, y'all, are just fractions. The definition looks a little bit disturbing, but it's just a fraction. P over Q, where P and Q are integers, and you know what integers is, positive and negative numbers, And Q can be 0, because you can't have a fraction with 0 in the denominator. So anything that fits that criteria is called a rational number. Any number that can be written as a fraction or a decimal. A decimal that doesn't go on forever and doesn't have a pattern is considered a rational number. Okay, then another type of number is called an irrational number. Of course, if you have rationals, you can have irrationals. And irrational numbers are numbers that cannot be written as a fraction. For example, the square root of 2 is a popular irrational number. Another one, I know you know, is pi. We think about pi as 3.14, but really it's a whole lot more than that. That decimal goes on and on forever, and it doesn't have a repetitive pattern, and that's an indication of an irrational number, a number that cannot be written as a fraction. And finally, we have the real numbers, and the real numbers are a combination of the rational and irrational. So it's all the numbers that we have worked with so far in any of your math classes. You might have heard of imaginary numbers. Those are not real numbers, but anything else you've worked with, any kind of fraction, positive number, negative number, square root number, all those are considered the real numbers. And basically, you need to be familiar with the types of numbers so you can create sets of your own and know how these things are discussed. So this is why you need to know this. Now, the cardinality of a set is the number of elements in the set. So that's called the cardinal number, and it's denoted as n of the set name. So say, for example, we have the set A is equal to 2, 1, 5, right? So n of A denotes the cardinality, or the cardinal number of the set. How many elements does this set have? It has 3. Okay. Now, if any of the numbers were listed more than once, you wouldn't count them more than once. Okay. So if I listed 2 twice, I wouldn't count it twice because it's really just a single element. And so let's do some examples where we're calculating or finding cardinality. So the first example, K, it says find the cardinal number of the following sets. Notice I have a -3, a 4, a 6, and a 19. I have 4 values or 4 elements in this set, so I would say n of k, but I got to get my pen back to do that. So I would say n of k, stand by, here we go, n of k is equal to 4 because there are 4 elements in this set. Next example, the set R, I have a 1, a 3, a 1, a 2, a 3, a 5, right? But we're not supposed to count the repeats. So really I have a 1, a 2, a 3, and a 5, and nothing else. Even though 1 was listed twice, I only write it once. 3 was also listed twice, I only write it once. So if I say n of R, that means the cardinality, or the cardinal number of the set R, is 4, because there's only 4 distinct elements in that set. And the next set is interesting. It says it's the set with 0 in it. And y'all, that's not the empty set. That's the set with the number 0. So I would say n of m is equal to 1. Well, check out the next example. The next example is a set with the empty set symbol in it. Now, does that mean that set is empty? Nope. It has the empty set in the set. So n of t is also equal to 1, just like m, because there's 1 element in the set. On the other hand, this guy right here, the set B is the empty set, has a cardinality of 0. So I could say n of B is equal to 0 because there are no elements in this set. Make sense? I could also say B is this. There are no elements in that set either. It's the same, it's different notation to denote the same idea. Okay, and then the last guy down here, 1, 2, 3, 4, 5, 6, and notice the dot, dot, dot. Again, that notation is called an ellipsis. There are ellipsis dots. That means we're omitting some of the elements, but you can always omit elements if you can follow the pattern. And we clearly see that the pattern is 1, 2, 3, 4, 5. How many elements are in there? Well, this is an infinite set. It goes on forever. So the cardinality, so this is cardinality, and cardinality can be infinite. Now, one more thing I need to tell you. Sets are equivalent if they have the same cardinality. Okay, so let's pay attention to exactly what this is saying, because we have equal sets and equivalent sets, and that's different. Equivalent sets have the same cardinality. In other words, they have the same amount of elements in the set. But on the other hand, sets are equal if two conditions are met. So notice, what are these two conditions? The first thing for a set to be equal is every element in one set has to be in the other set. So if you're saying A is an equal set to B, then every element in A must be in B. Hey, but also every element in B must be in A. Now, I know that seems obvious, but you really have to check for this to be able to tell if sets are equivalent to each other. So another way of saying that, this is the same thing as saying A and B have exactly the same elements. And that's regardless of order. The order doesn't matter. If sets are in a different order, that's perfectly okay. But say, for instance, the set A is equal to 1, 2, 3, and the set B is equal to 3, 1, 2, A is equal to B, because why? Every element in A is also in B. So 1 is in B, 2 is in B, 3 is in B. But also you got to do it the other way. 3 is in A, 1 is in A, and 2 is in A. I hope that makes sense. So those are equivalent sets. And for our last example, I have a true-false here, okay? And I want to look at different sets. So, is the set 2, 3, 4 the same? Is it equal to, not equivalent. Equivalent means they have the same number of elements. Are these equals? And so notice the equal sign. This is set builder notation. X, such that X is a counting number between 1 and 5. Now let's think about this. What are the counting numbers between 1 and 5? And if we do this in list form, between 1 and 5 means we don't include 1 and 5. It doesn't say odd or even counting numbers. It just says all of them. So that's 2, 3, and 4. Is that the same set as 2, 3, and 4? Yes, it is. So that's a true statement. Now, a second example, 11 and 12 is the first set, compared to X is an even counting number between 10 and 13. Okay, now the counting numbers between 10 and 13 are 11 and 12. But notice it said an even counting number, so 11 is not part of that set. So is 11, 12 equal to the set 12? Well, clearly not, because the second set over here is missing the 11. So this is definitely a false statement. And for our last problem in the lesson, we've got the set of, notice this is ordered pairs. So 0, 0 is an element, 1, 1 is an element, and 2, 4 is an element of the set. And look, I forgot my little curly brackets right there. Now it's in set form. Now in set builder notation, it's saying all the xy's such that x is a natural number less than 3. So let's talk about the natural numbers less than 3. That natural numbers, remember, are counting numbers. So 0 is not included. That's 1 and 2 are the natural numbers less than 3. And y, the second value, is equal to x squared. Okay? So if y equals x squared, remember this is x, so 1 squared is 1, and 2 squared is 4. If I write that in ordered pair form, that would be 1, 1, where 1 is the natural number, and then 1 squared is the second number. And the next one would be 2 and 4, where 2 is the natural number, and then 2 squared is the second number. Is that the same? No, because this has got a 0, 0 in it, and this doesn't. If they would have changed that word to whole number, they would be the same set. But since that doesn't say whole number, that is a false statement. The last one was a little bit confusing, I know, but again, notice the ordered pair says natural number first, and then the square number second. I hope this helps. Please contact me if you have any questions about this section or anything else in the course. I hope you have a wonderful day.